Hello, my name is Monique Dali. We developed at LMMP in PUC-Rio a numerical model for simulation of flow in saturated poroelastic media with isolated vugs. The motivation for this research relies on carbonate reservoir, which presents pore space at different scales. Conventional computational fluid dynamics solves Stokes in heterogeneous porous medium to estimate average properties of rocks. However, it leads to a problem of geometric scale, due to multiple pore sizes with thin channels of micrometer and large voids of centimeter size, what makes the solution extremely expensive in terms of computational cost. Alternatively, on core scale perspective, the flow can be described by Brinkman equation that gives a simpler transition between Stokes free flow region and Darcy's domain with a given permeability value for the porous matrix. With a single equation to describe both domains, we avoid the imposition of a boundary condition at the interface. No matter which option we choose, solve the flow problem numerically is not an easy task. The objective of this work is to develop a 2D numerical code for flow in saturated poroelastic matrix with the presence of vugs. In previous work, we implemented a direct numerical simulation in rigid porous media with the Brinkman model that uses a fictitious domain approach to recover Stokes or Darcy. Combining this previous knowledge with elastic deformation of the solid, the desired model coupled mechanics and flow in porous media. Then, when the material is deformable, the structural deformations affect the flow and pressure, and the fluid flow and pressure fields affect the structural deformation. Thus, we want to obtain equivalent permeability and solid displacement. The single domain approach using Stokes-Brinkman equations provides a model that can be continuous varied from a Darcy-dominated flow to a Stokes-dominated flow. The mathematical model is derived in the framework of Biot's consolidation theory for poroelastic media, including force equilibrium of solid skeleton, Darcy's law for velocity, and mass conservation of fluid. For time discretization, we apply the conventional backward Euler scheme. As the system is now composed of a deformable porous medium, we combine Biot-Brinkman equations, then we substitute Darcy's law by Brinkman and include mass conservation at vug domain. For pressure, fluid velocity, and solid displacement are chosen as primary variables. In this work, we proposed a coupled solver to account for the interaction between fluid flow and geomechanics using the mixed finite element method. The weak formulation for this system of equations is implemented in Python with Phoenix library collection to numerically solve the horizontal flow for the 2D domain subject to solid deformation. The geometry is then discretized in appropriate finite element space. The simulation of poroelasticity problems is very difficult because of the coexistence of different physics that require coupling. We employed two coupling approaches, the full implicit and iterative scheme. We implemented the full implicit approach for Biot's equation. This approach solves simultaneously the two phenomena, porous flow and mechanics, resulting in a very large system to be solved at each time step. Since the iterative scheme split the system into a flow problem and a solid deformation problem, it results in two much smaller problems and use some correction terms to make sure that the equations are solved at the same time step. To avoid splitting errors, we control the tolerance of the convergence. This method was implemented for Biot's and Biot's Brinkman's equation. In previous work, we investigated the validation of the Brinkman equation. We ran some simulations to compare our numerical flow model with the LDA experiment presented by Yao and Wang. Also based on Beavers and Joseph's experiment to check the interface condition in the transition zone between a channel and a porous material. The equivalent permeability obtained with the flow experiment in porous medium with a drilled vug by Lasso et al. Were used to further validate the flow model. The similarity between our numerical predictions and the experimental values confirms that the Brinkman equation can be correctly applied to capture the physics of single-phase flow of regular porous medium at Dali scale. developed code was submitted to two benchmark poroelastic problems, the Terzagh's 1D problem and Mandel's problem, both with available analytical solution. The fully implicit iterative couple scheme were implemented for Terzagh's problem. The top surface of a saturated poroelastic medium is assumed to be fully drained, while the bottom surface is impermeable. As for the solid part, the bottom face is fixed and the top surface is exposed to a constant vertical load. The sudden increase in load will be initially suffered by the fluid, and thus the water pressure goes up in the column. The dissipation process may take considerable time, depending on the permeability. The pore pressure dissipates continuously since the top surface is fully drained until vanished. Then the load is supported only by the solid matrix. On these graphs, we can observe the agreement between our numerical data and the analytical solution. The computational time for fully coupled scheme was around 15 hours and 10 hours for the iterative scheme. To analyze the accuracy of the model, the absolute error was calculated for each time curve. The highest deviation was 1% for fully implicit method. After numerical validation of the poroelastic model, we designed a simple artificial porous medium composed of a single circular inclusion to mimic VUG and capture clues about what affects the equivalent permeability. The integral over VUG area is based on the Stokes flow, while the porous medium area is related to Biot's equation. The geometry is then discretized in appropriate finite element space. On the left and right boundaries, Dirichlet homogeneous boundary conditions were imposed for the displacement of the solid matrix for zero normal poroelastic stress. Both sides won't move in the x direction. A natural condition for pressure was also imposed on this boundary, while at the top and bottom we imposed the impermeable condition for the flow. Permeability of the porous matrix was updated at each time step as a function of load. This video shows the numerical results for the pressure, flow velocity, and solid displacement fields. Initially, the porous medium is saturated. With the compressive load at top and bottom walls, the fluid starts to be expelled from the domain by inlet and outlet boundaries. When the vertical loads remain constant, the fluid expects to flow from left to right direction. We can see the contraction and expansion of the top of the domain after removing part of the load. This demonstrates the required reversibility of the numerical model. To show the model's ability to replicate realistic scenarios with interesting poroelastic behavior, the model was applied to a two-dimensional problem of single-phase flow in core samples. To make it possible, we first acquired a CT image of a carbonate sample. Next, we segment the image, create meshes, and apply the developed simulation tool to solve flow in 2D slice. After post-processing step, the equivalent permeability is computed. A bounding box composed of homogeneous porous matrix with same permeability was virtually added to the two-dimensional slicing taken from the meridian section. This frame addition was due to the possibility of voids close to the load application region, which would result in an exaggerated edge deformation at this location. A few time steps after the application of maximum load, a new equilibrium on the flow is reached. The computational wall time for the iterative scheme with around 57,000 triangular elements was around 13 hours. Summing up, in this work, we have developed a coupled 2D model for flow geomechanical simulation in porous media. The fully coupled and iterative approach are successfully implemented. The performance of the numerical poroelastic model is validated according to Terzagh's 1D problem and Mandel's 2D problem. In all cases, our numerical results show good agreement with the analytical solutions. With this simulation tool developed and validated, we could apply in some situations. The model was submitted to a single VUG cell in realistic scenarios based on carbonate samples with poroelastic behavior. Finally, I would like to thank all the financial entities that supported this work, and thank you for your attention.